Okay. So how many of you all have gone through the contents of week 9? Can I get a show of hands? Okay, all right. So in the previous session, we went through the contents of primarily decision tree, how a decision tree works. We saw its documentation in Kaggle, and then we ran it through a data set. So today we'll see a bit more on that. But before that, let's first go over the other second half of the content that is there in week 9, which is on the different evaluation metrics. Okay, so firstly, can someone tell a few of the evaluation metrics that we see for classification problems?
Accuracy, precision,
Okay, so
um,
we have accuracy, precision,
precision, recall, and F1 score.
recall,
F1 score.
F1 score. Okay.
Yes.
So yes, these are some of them. There are a few more that are used in practice, but today we will go over these four specifically. We'll try to understand them fully from a perspective of working on classification related data sets. So, what would be the formula for accuracy? Or you can first tell it from a binary classification perspective. Let me set some context. So, there are two classes, which is also called as labels. Let this be 1 and 0. Here I'll call 1 as the positive class and 0 as the negative class. Okay. So now can someone tell me what is the formula for accuracy first?
True positive plus true negative divided by the total.
Okay, true positive plus
True negative
true negative.
True negative divided by total
by
number
the
of
number of points.
Okay, divided by total number of predictions, right? So we can say that it is true positive plus true negative plus false positive plus false negative. Is this correct?
yes, sir.
So in general, can I say it is a ratio of correct predictions, made divided by total number of predictions made. Just write total predictions. Now for this, what we need to understand is what is true positive, what is true negative, what is false positive and false negative. Actually happens to be fairly straightforward. So what is true positive? I want to hear from you guys.
The actual and the predicted values are positive.
Okay, actual class is positive,
The
predicted
predicted
class
is also positive.
is also positive. What is true negative?
And actual class
Actual classes belong to negative class.
Okay, actual class is negative class, and what about predicted class?
is also negative.
Okay. actual class is negative and predicted class is negative. And what about false positive?
Yeah, actually, it's negative on the predicted.
Okay. So actual is negative and predicted is
Positive.
positive. So false negative.
Yeah, actually, it's positive on the predicted is negative.
Okay. So it's good. So this is a very simple, straightforward thing. I'm sure many of you all might know it, but unfortunately, with time, people tend to sometimes get confused with it. So I hope this is clear for all of you. So for this part, if at any point if things are not clear, you can stop me right then and there. And now in this particular problem that we've taken, what we've decided 1 as positive and 0 as negative. So let me take an example, confusion matrix for this. So I'm going to draw a confusion matrix. Okay. So let's call this as 1, 0, 1, 0, and this is going to be predicted, and this is going to be the true. Maybe we can start off with some simple numbers. Okay. So here, how many true positives are present?
25.
True negatives,
25.
false positives,
5.
are you sure?
Yes, 5.
Are false positives 5? What is the definition of false positive? Actual class is negative, predicted class is positive.
Okay, it's 10 seconds.
So false
Sorry,
negative
10.
is 5.
10.
So let's maybe revisit it for. So firstly, what does this 25 indicate? So your true label is 1 and your predicted class is 1, which was our definition for true positive. The next easy one is your true label is 0, predicted label is 0, or in this case negative. So this is true negative, right? And then if you come to this cell, this is where the true label is 1, but predicted is 0, or rather the true class is positive and the predicted class is negative, which is what we have here. So it is false negative. Likewise, the remaining one is the true label is negative, but predicted is positive, which is what we had here. There's nothing but false positive. In general, the way I tend to kind of in the beginning at least I should do it is false positive is falsely predicted as positive. I mean, I used to think of it like this: falsely predicted as positive. Likewise, for negative, falsely predicted as negative. So at least that is how I used to think of it. It's up to you guys how you want to go about it. So now that we have these values, will class 1 always be positive and class 0 always be negative? So the way I phrase this question should probably tell you the answer for it. But what do you think is the answer?
Sorry, can you repeat it, sir?
Yeah, so here we have taken class 1 to be positive and class 0 to be negative. But is that a rule that we have to follow? Okay, so
Not
when I'm getting at
necessarily.
this, yeah, so exactly, it is not necessary. So this is just a matter of convention. If I wanted to, I could take class 0 to be positive and class 1 to be negative. So in that case, these things would just get reversed. Okay. So whenever you are asked a question as to what is the, say, precision, recall, false positive, false negative, and so on, the first thing to establish is what is my positive class and what is my negative class. Okay. So for the lecture today, or for the discussion today, we are going to always take class 1 to be positive and class 0 to be negative. So, but in your projects and any work in your Vivas, always make sure that you have clarity on what is the positive class and what is defined to be the negative class. Okay, so with this, let's first go over the first metric, which was accuracy. So what will be the value for this?
Divided by
50 by 65.
50 by 65. So I've gone for a more comfortable number, but regardless, this will give us some value. So what we have just done is true positive plus true negative divided by all the predictions made. Okay. So this will give us some value. We make it to come to 75. So 50, 60, 65, we need 10. So let me just make this 15. It will probably become a problem elsewhere, but okay, at least for this one, we have 50 by 75 now, which gives me an accuracy of 52 by 3.66, whatever. Now that we have figured out what accuracy is, we've had this discussion multiple times, but I would like to know what is one situation where accuracy is a bad metric.
we have imbalance data set.
Okay. So accuracy is a bad metric when the data set is imbalanced. So here itself, if I were to modify this example for the same case, I could say there are, let's take some, maybe take a copy and let's try and work with this example. There are
Sir, can you
75
scroll up
points.
once?
Yeah. Is there a doubt?
Okay, done.
So there are 75 points. 70 belong to positive class. Call it 1, and 5 belongs to negative class, which is 0. Okay. And I'm going to modify this to showcase our example. Here we know that the data set is now imbalanced, and I'm going to say the model predicted this way. Now what is the accuracy?
70 divided by
70 by 75, right? Because the total predictions are nothing but 70 plus 0 plus 5 plus 0. This is very clearly a high number, whatever this comes out to be. But we know that this is a pretty bad model because it has just predicted everything to be the majority class. So here we see that accuracy is a bad metric. Okay. So with that, let's come to what might be a good metric. Let's try and first do it in the context of this one. Okay, we have these values, and now let's start with, say, precision. What is the formula for precision?
This is true positive by total positive or true negative by total negatives.
Okay. So what do we mean by true or total positives or total negatives is the thing. So this time I'm going to ask precision for class 1, the positive class. In that case, what would it be in terms of these four values? So you have gotten the part of it is true positives, correct. What should go in the denominator?
Total positives, which is 25 plus. What's positive? It is that's negative.
Total positive plus false
Plus
negatives.
false negative.
Are you sure it's false negative?
Yes.
false.
Means it should be positive, right?
So it is false positive. So precision is true
False
positives divided by how many were predicted positive.
predicted positive.
Okay. So once again, in general, I go with true positive divided by predicted as positive. So if it is predicted as positive, either it should be true positive or it should have been falsely predicted as positive. Okay. So this is precision, and what is the value in this case?
25 divided by 25.
25 divided by 25 plus
10.
10. So this is the 25, this is the 10, because this was true positive and this was false positive. So this value comes out to be some 25 by 35. Right. Okay, so is precision okay? Clear? Any doubts? All right. Let's go back to this being a bad metric example. Okay, so we had established that accuracy is a bad metric, but let us find precision for class 1. What was the formula? It was true positive by true positive plus False positive. Correct?
Yes, sir.
What is the answer in this case?
70 divided by 75.
70 by 75. Anybody else with any other answers? Okay, so we have established that this is the precision value. And once again, unfortunately for us, this comes out to be a very high value. It actually happens to be about 0.93. Now, we are in the same problem as with accuracy. So this value has again given us exactly the value of accuracy to be in the case. So does this mean precision is a bad metric, or where are we going wrong? Or what are we missing from this? Any thoughts on this? You can say whatever comes to your mind. With accuracy, we saw that problem. When
No,
it was
here it
imbalance.
doesn't really do bad. Right? The precision is okay only because
Yeah, but would you say this model is good based on precision? So I'm going to put
still
this.
good, right? Because totally 75 observations, out of which I am good 70 times.
Is the
It is
model
precise.
is the model good? Good is a very subjective term.
Based on precision, yeah, it's good
Based
for
on
this.
this confusion matrix. Okay, now I want you to make a general comment. So, generally, do you think this model is good?
I tried to predict 75, out of which 70 is good.
You call it a
What
good
we
model?
positive only, even though 5 negative classes are there.
Okay, could you speak a little louder? I only got it partially. What you say, Prashant?
Yes, sir. The total values are predicted are completely positive. So,
Right.
even though negative classes are present.
Correct. So that's the thing. Even if we got a high value, we can say that these 70 values were correct. But imagine this to be the case. Imagine, say, if there is one, if the let us put an event behind this. If it is one, there will be no earthquake. If it is 0, there will be an earthquake. In the context of this, would you say this model is good? 70 times it has got the predictions correct. But would you agree that these 5 can be very costly?
Of course.
Yeah, right? So, which is why, while it of course depends on context to context,
It
but
depends
a
on the
model,
consequence.
yeah, but a model that always predicts in one class, regardless, is a bad model. Because if it always predicts the majority class, why would you need a model in the first place? Why do I need to pass in the test data to that model? Why do I need to continuously rely on it? While I can simply say just predict everything to one class. Right? Because the fundamental idea with which we came about the need for machine learning is wherein it should not be a task that is algorithmic or formulaic in nature. It's not something that we can directly say do this, do that, but we wanted to have it find some underlying patterns and try and approximate some function and so on. So regardless of the context, this is a bad model if it always predicts one class. And in this context, especially when the cost of there being false positives, or rather, yeah, the cost when there can be false positives if it is high, then it is an especially a terrible model. Okay, so that is one thing. And now, with that in mind, we saw accuracy was not good enough. given this confusion matrix, we saw that relying on accuracy is not good enough for us. So we next came to look towards precision. But even when I calculate precision, this is the value I'm getting. And 0.93 should make me think that this is a good model, but we've already established that it's a bad model. So what is it that I'm missing here? What should I look towards next? So you are working on a data set. You can say that this is the exact confusion matrix you got. You first calculated accuracy. You saw it was a high score, but based on confusion matrix, you realize that accuracy is not working out. So you want to turn towards other metrics to convince your boss or your some stakeholder that this model is not doing well. So you go for another metric, and you saw precision also turned out to be like this. So where are you going wrong? What are you missing? What should be your next step?
We have
established precision for class 1.
Okay.
Maybe we can check for class 0.
Perfect. So this is the thought process I would want you all to build while you are working. So here what we have calculated is the precision for class 1. Now if I were to switch to precision for class 0, what is the formula? How does it change?
2 negative divided by 2 negative.
2 negative plus?
False negative.
Perfect. So what is the value?
Zero, sir.
Yeah, so it is 0 by 0. Of course, it goes to, strictly speaking, it is like undefined or whatever. But the point is that this shows that precision for class 0, it is just 0. It sort of finalizes that this is a terrible model. So which is why we come back to an important part again, that your precision is always, we calculate it class specific wise. And even when you do the sklearn implementation, it will show you for one specific class. So it is always important that, but when you do the classification report, however, you get the values for the other classes as well. So precision was the other metric where we saw this particular case, wherein if you put everything, if you predict everything as a positive class, and if your evaluation metric is precision, you can still get away with a high score despite your model being bad. Now with this intuition in mind, I'm not going to go in detail for the other two, that is recall and F1 score. But regardless, maybe we can just quickly discuss the formulae for it. Yeah, what is the formulae for recall? Recall for class 1.
True positive divided by true positive divided by false negative.
True positive divided by
True positive plus false negative.
true positive plus false negative. Anybody else? Any other answers? Everybody agrees? Yeah, so this is correct. So in the case of recall, it is almost with all these metrics, the numerator is going to be the true value of that class, either true positive or true negative. And in the denominator, this says how many of them were actually, or how many of them were really, positive. So you have true positive divided by true positive again, plus it was falsely predicted as negative, but in actuality it was positive. So that way this is recall. And in this particular case, what will be the values? What is the value?
25 divided by 25 plus
25 divided by
25 plus
25 plus 15. Right. I hope there's no other doubts. So this gives us again some value. Similarly, we can calculate the recall for the other class. Whatever we discussed for precision continues to apply here as well. Okay, if we take that other imbalanced case. Then let's also do F1 score here itself. What is the formula for F1 score? Firstly, what is F1 score?
harmonic mean of precision and recall.
Right, it is the harmonic mean of precision and recall. So it comes out to be 2 by 1 by precision plus 1 by recall. Okay, this is nothing but the harmonic mean of the two quantities. Now I can sort of do some simplification here, and I can write it as 2 into precision into recall divided by precision plus recall. This is just your formula for F1 score. Now here let's do one other thing. So we had this example, right? Let us actually calculate the recall for class 1. So recall for class 1. What is the formula once again? What goes in the denominator?
2 positive plus 1 negative.
So especially when you are going for your MLP project, YOAS, or for any projects, it doesn't matter how many times you repeat this, you properly understand this, and if someone wakes you up from sleep, shows you a confusion matrix and asks you to explain it, there should be no confusions about it. Okay. So for this particular calculation, true positive is 70 divided by, again, true positive is 70 plus false negative is 0. And for the other class, if we do recall for class 2, it is going to be true negative divided by true negative plus false positive, which is going to be 0 by again some 0 plus 5. So it is 0. So here it is 1. So I can see the difference, and that way when you actually calculate your F1 score, you are going to end up seeing that it is going to be a better representative because it takes into account both these things, and for one of them it is going to be extremely terrible. So this was mainly with these few metrics, and of course this is all in a similar fashion it has been done in the lectures, but for completeness sake for this week I wanted to go over this. We'll do one last exercise, which is to extend this to a multi-class classification setup, and then we'll do some coding and work on a data set. Among those who joined late, I think Hema, Prashant, Ravi and Sudhir, did any of you all work on the Kaggle dataset? Did you all get a chance to do it?
No, sir.
Okay. What about Prashant, Ravi and Sudhir? Same answer?
Yes, sir. Yeah, right.
Okay. All right then. So to you all who have joined later as well, do make sure that before the end of the course, at least once you all work on one of these Kaggle data sets, and as you spend time with it, you'll understand how much it helps you. Okay. So maybe the next week, I think next week I'll be there again for the sessions. Probably by the Thursday session. I understand that Sunday is the quiz. By the Thursday session, try to work on the data set. Okay, meantime, let's finish this.
So can I scroll once up?
Yeah. This is for a multi-class classification setup. So now I'm going to put in some random numbers. Okay, so now we are in a new dilemma, which is, so far whenever we discussed, we had a well defined that class 1 is positive, class 0 is negative. How do we go about it in this particular case? First, let's start with the three metrics. How do I calculate accuracy now? Any thoughts?
The combination of the center ones, the diagonal ones divided by
Okay, can
the
you
total.
read out the numbers for me?
10, 15, 10.
10 plus 15 plus 10. So he was referring to these three numbers. Okay. And what goes in the denominator?
The total.
The sum of everything. So I'll do it row wise. So it is 10 plus 3 plus 4 plus 4 plus 15 plus 1 plus 1 plus 2 plus 10. So this gives us 35 divided by 13, 17, 21, 31, 36, 37, 38, 40, 50. I hope my calculations are correct. So if it is so, we get an accuracy of something like 0.7. Is this okay, clear to everybody? So here, what we'll again see is there's a general pattern. That is, accuracy is always number of correct predictions divided by total predictions made. So that way accuracy was straightforward for us. And luckily for accuracy, we don't see class 1, class 0, class 2, what it is. We just do it collectively. But now what do we do with precision? So how do I calculate precision? I come and tell you, okay, you have to calculate precision. What are you going to do? Recollect what you did what was the approach in the previous case, in the binary case. And we have to logically, we'll try and extend it to the multi-class setup. Yeah, what do we do?
Take all the true values and divide it by true positive.
Okay. So firstly, I told you there is some step that you have to do when you are asked to calculate precision. So what is it? What do you need to do before you calculate precision? You are told you have to calculate precision, but what is the clarification that you need to get?
We go class wise, sir.
Yeah, so we have to go class wise. So the first clarification you need is which class are you calculating precision for? Here, since we have 0, 1, 2, let me start with 0. Now, what was the formula previously? So imagine there were two classes and you were asked to calculate it for the positive class. What would the formula have been? What goes here for precision? True positive by true positive plus?
False positive.
False positive. So now when I'm calculating precision value for class 0, what I'm going to do is I'm going to assume that this guy, oh, mistake here, this is supposed to be true label, predicted label, true label. Okay. So when I'm calculating precision for class 0, I'm going to assume that this guy here is my positive class and these two guys are my negative class. Okay. So with this assumption in mind, what is true positive? The true label should be 0, predicted label should be 0. How many values are there?
10, sir.
10. So again divided by 10 I'll have. And false positive is how many times I've falsely predicted it as positive. How many times has it been some other label but I've predicted it as 0?
5.
How is it 5?
4 plus 1.
Perfect. So if you'll notice, there are these values here. Their true label was something else, but I falsely predicted it as 0. So 4 points that belong to class 1 were given label 0, and 1 point that belonged to label 2 was given as 0. So which is why I now come back to 10 divided by 10 plus 5, nothing but 10 by 15. Once again, some 2 by 3.67 value we come. So now if you will correctly tell me what the value is for class 1, then we will not calculate it for class 2. Directly the numbers. What is it for class 1? Precision for class 1.
15 by 20.
15 by 20.
20.
15 plus what should go here?
3 plus 2.
3 plus 2. So the 3 here and the 2 here. So we have a 15 by 20 as our answer. 3 by 4.75. Similarly, you will calculate for class 2. Now, the other guy we have is recall. So recall for class 0. What should be the values for recall? Firstly, what is the formula for recall?
True positive divided by true positive. False negative.
True positive by true positive plus
False negative.
False negatives.
super. So then what are the values for class 0?
10 by
10
7.
divided
10 by
10 plus
17.
10 plus
okay. 10 plus
7.
7.
just 3 plus 4. Because now we are looking at these guys. So 10 is the true ones, and 3, the true label was 0, but it was misclassified as 1, and 4 values, true label was 0, misclassified as 2. Hence you get your value 10 by 70, which goes to whatever value. So this way, for precision recall, we calculated individually for the classes, and then for F1 score, again we use the same setup, same formula that we used here. Once you find your precision and recall for the classes, you can calculate the F1 score as well. Any doubts with this? Any doubts with what we have done so far? Okay, all right. Great. So in that case, we'll finish up the little parts that were remaining from the last time and try and close the session early. Okay, so this was the notebook we were working with. Loading. Okay, so I've run this file from the beginning. So whatever, in case you all have not seen this was covered a bit in the last session. So once it loads, we'll just quickly go through it. Reading the files, looking for null values, the initial few rows, the ranges for the different functions, data types and missing values, checking for if the data set is balanced. Then we did a heat map with the correlation values. Did some box plot for one of the features, split it into train and test. Checked if both the data sets have a similar distribution. We spoke about stratified splits there. Then we built our decision tree model. And we did the classification report. And this was the corresponding confusion matrix. Right, so we discussed this today mainly. And the other parts we discussed in the last session. Let me move it to a different section. Okay, we'll come to this. So now what was let's calculate the precision for class 0. Manually, can you look at this and tell me what are the values? Class 0, what is the precision?
70 by
70 by
111,
which is 70 plus
41.
41. Everybody okay with this? This is the true positive divided by true positive plus false positive. This is precision for class 0. So recollect that in this case, now we are just mentioning class 0 as the positive class. So let us also import it from sklearn dot metrics. Import. I think it's just precision. It's not precision, is it? Is it precision score? It is precision score. I'm going to say print precision score for, is it y test comma y print? Y true comma y print. So the true values will be y in y test and the predicted values in y print. So we did this the last time. So you can see here ytest is our original label, ypred is the predicted label, and it has given us 0.85. Let us also calculate for the other class, because it looks like it has taken 1 itself as the positive class. (278 by) what should it be? 278 plus 49. This is for class 1. Precision for class 0. For class 1 is 278 plus 49. So I'm doing this column. Okay, so it is 0.85 here. So okay, so here there was a mistake in what I said, in the sense that sklearn treats 1 as positive class and class 0 itself as negative, but in general it is something that is to be described. So I'm assuming it should be there in the documentation somewhere. So they'll probably call class 1 as positive and class 0 as negative. We have to check the documentation for confusion matrix as well as this one to see what is the sort of template they are following. Okay.
So there is a parameter above. Positive underscore label.
Yeah, it is given here. Perfect. So here it is given that pos label is equal to 1. So in that case, I should just be able to change things here as well. Perfect. So when I change the positive label to 0, it changed to 0.63. This is why it should again convince you that it is just a convention, and by default they go for 1 as the positive class, but it needn't be so. Okay. So similarly, let's also do recall and F1 score. Okay. Let's also calculate for class 1 itself. Let's calculate this time. What is the recall for class 1? What should I write here?
278 divided
By
278 plus 41.
278 plus 41. So this is true positive, and denominator for recall is how many of them were really positive or actually positive. So it is 278 plus 41, because this is the true label row wise. I got the value 0.87, and I should see the same one when I run this. You can see the first value is 0.87 for recall score, and the F1 score is 0.86. To get all of this collectively, we simply look at the classification report. Now we run the code cell below here. Okay, as you can see, we got the precision for class 0 as 0.63, which is what is there in the report. Then we got precision for class 1 as 0.85, which is what is here. Then we saw recall for class 1 is 0.87, which is here. And F1 score for class 1 is 0.86, which is here. And also with the points, so if you see how many points belonging to class 0 are there, it is 70 plus 49, which is 119. This is what you see here in support. And the same thing goes for class 1. So the F1 score is there, the overall accuracy is present. And then macro average and weighted average, I think it is also discussed in the lecture. So this is about a combination of these things to get a value. The other is to weight it as well. So you can read more on this in the documentation as well. Be there here. Yeah, so there is micro average, which is on the base of label, and weighted average. So roughly speaking, this takes into account how many points belonging to the different classes were there. Depending on the support value, which is what you see here, it is going to weight the values that you get here. Okay. So that is roughly, I think, could maybe show it as well. Yeah, so you see these two values. The value that I've done is for macro average, which is just the average of these two guys, 0.63 plus 0.85 by 2 and 0.59 plus 0.87 by 2. Weighted average just weights these values by taking the support into account. Okay, so that is the only difference. It is like the weighted average. Okay. So this was the evaluation metrics. There was one more thing I wanted to present for today. So we have built a model. I'm hoping it was called model itself. Yeah, it was called model. Let us see for decision tree.
This macro and weighted, what kind of weighted average, what kind of weight it takes?
So weighted average is by taking the support into account. If you recollect, in decision tree in MLT, we saw this when we were calculating things like information gain, we were weighting the number of samples that came, right?
Yes.
So this weighted average also is a similar kind of weighting, wherein if one of them, like for example, class 0, if it had very few values, and if class 1 had a lot of values, then the impact of both of them should not be treated as the same. So that is the ideology behind weighted average. Macro average is in the bigger picture, you just take the values that you got, in this case 0.63 and 0.85, and you just take an average. Now for this guy weighted average, it also takes into account how many points were present. Okay.
Okay.
So it is depending on how many points went in here. So let's see if it is like this.
And based on this, what kind of insight we can have?
So it is again depending on the problem statement how you want to make use of these values. But if your data set and all is say highly imbalanced, and if you want to take this into account, you can again say that the value that you have obtained for this, like if someone asks you give me a single value. Now I showed an example where the precision when we did it with the while writing, we saw that the precision for one class was high and for the other class it was very low. In that case, rather than saying I got the precision for class 1 as this one and class 0 as this one, if I tell you just give me one value and say if the precision is good, you can go for this average, a macro average. Same way, if you want to go for weighted average, especially useful in the case of imbalanced data sets, you can present it this way as well. We just verify this. So as you can see, this 0.63 that is there now, it is taking into account how many values were there here. Now suppose, let me change this to, say, let's make the precision for this very low, and for this one we'll keep it quite high. So in that case, if one class say had a precision value of close to 0, I'll write something like 0.1, and the other class had a high precision, say 0.99. Okay. And now if I take the macro average, you can see it comes down to 0.545. So now I can tell that, see, even though your precision for one class was high, collectively, if I see the precision values, if I take the average, it comes down to this much. And the same thing I can do in the case of weighting it. So I can now say 0.1, and this one I can say as 0.99. Now, since there are a lot more points in this, it will still end up giving a higher value overall. So now see, it is 0.74, it is higher than this one. While macro average did not take into account how many points were there, it just gave you an average value. Here you want to say if there are more points belonging to one class, their impact should be more. If your problem statement necessitates that that is the kind of value that you need to communicate, then this is what you would go with. For example, now in this binary classification, it might not be very nice. But if I go to a multi-class setup and say many of those classes had very few values. Now in this case, if say this guy had just 5 values out of the 438, and this guy had say the remaining 433 values. Now the value is still close to this guy. It's close to this 0.99, that is it is 0.979, because this guy had more points, so we wanted to listen to the impact of those many points. Now in a multi-class setup, maybe I had 10 different classes. It performed poorly on, or rather for most of the classes, the value was low. But the one class where it predicted properly was my important task. So I don't want the entire calculation to be brought down just because of how it performed in the other classes. I wanted it to be weighted based on how many samples were actually belonging to this specific class. Okay, I hope I gave a rough intuition. If not, I would say take a multi-class setup. That Wine dataset has many classes. Run the classification report, and that should give you a better picture. Is that okay?
Yeah. On the multi-class, it will help a lot.
Yeah. Okay. So coming back to this part, so we built a decision tree model, and let us see some of the attributes. Let's start with simple one. How many classes were present? It says there were 2 classes, 0 and 1, and again in classes is the same. Let's do this. Okay, so these were the features. These were nothing but the features of our data set. We saw this last time as well. Now, one of the things we discussed last time, the advantage of a decision tree model is how interpretable it is. So one of the reasons why it is interpretable is once you actually build your model, you can visualize the decision tree. So in the case of sklearn, there is this particular sort of module called as tree, from which I think it was called as plot tree. So it is correct. So let's check this one. Let me see if I can directly call it here. Plot tree. So it takes the decision tree and it takes some other things. Let's pass in just the model first. It's generating the model. Okay, this is not very nice to look at. It is still running. Let's give it some time. Okay, it's run now. And this is the tree that we got. Okay, it is not very nice to look at. Let's reduce the depth and try. I'm going to change the model. I'm going to say model 2 is equal to decision tree classifier and max depth equals to 2. Random state is equal to 42. Then model 2 dot fit X train, comma, Y train. We have this new model, and let's see what it has done. Okay. So this is what it says. Now you can see that it is a smaller model, but let me see if I can improve the way it is presented. So if we can go to the documentation. So there is one of the parameters is actually to pass in the feature names. So let's do that. So we'll pass in the feature names. We can maybe even pass in the class names and all that. Let's see how it looks like. So what was our training data called? I hope it was called X first. Okay. So I can pass in the feature names is equal to X dot columns. Okay. So is it visible? Now here you can see it is visible, right?
Yes, sir.
Okay. So here you can see, if you recollect, we had these features called as cloud and dew point, and it is telling that the feature that it used to make the first split was whether the value of cloud was lesser than or equal to 73.5, and the Gini value that it got was 0.365. The number of samples initially were 1752, out of which 421 went to one class, 1331 went to the other class. Then the next split it made was whether the cloud value is lesser than or equal to 43.5. Those that answered yes went to one thing, those that answered no went to the other thing. Likewise, it did the same thing with dew point. Okay, so you can keep on changing some things with your model. So let's change some other parameter here. Let's do the criterion as entropy this time. Let's give criterion equal to entropy, and this does not come here. Here, and let me increase the depth to 4. Okay, and this time when we plot the tree, it makes it harder to read. Okay, let's go back to maybe 3 years there. Okay, let me see if I can increase the size. Here t dot figure. What's this? Okay, is this visible?
Yeah. Yes.
Now you can see when I change the max depth and the criterion, the split that I got also is on different ones. So firstly, anyway, the cloud thing remained as it is. Previously, we had cloud on the left side and dew point on the other side. But now we have cloud itself being used again. And in the subsequent one, it has even used other features like wind direction, max temperature, dew point, and pressure. Okay. So I hope you all can see the beauty of this. One is that the model that we built is actually present very interpretably as a form of a tree, where in detail we know everything about this model. Now, if I use one more thing, which is the parameter, I think it should have a feature importance. Yeah, it has a feature importances. Okay, so it is giving me these values, and let us put the columns. Of course, you can present this in a better way by having the names of the columns and these things together. So as you can see, ID is 0, day is 0, Pressure is given 0.16. Firstly, you can notice that there is 1, 2, 3, 4, 5, 10, 12 values, and here I think we have 12 features also. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, we have 12 features. Ideally, in the model building part, you could have removed ID and then built the model. But coming back to this, we see that the features that it shows as important are the third one, which is pressure, max temperature. Then we have, so temperature and min temperature is ignored, and then we go for dew point. Humidity is ignored and cloud is gone. And after cloud, we next go for wind direction. Right. So wind direction, cloud, dew point, temperature, max temperature and pressure, which is what is there in your this model as well. You have max temperature, wind direction, dew point, pressure, and cloud. So this is in general, or I would say, the most beautiful thing about decision tree, wherein you can see the feature importances and you can see it in this tree-like structure. And let's actually do this thing as well. Let's do this in a heat map. Reuse this code. Okay. So let's, we don't have the target here, right? What was the data called? It was called train. So let me plot the heat map for train. Just 1 second. Okay, so here if we see, the target variable was rainfall. It had the highest correlation with cloud, and humidity a negative correlation with sunshine, a bit with wind speed, and then with the rest of them it was not so much. Now one thing has definitely matched, the cloud having a high value, we can see here there was a strong correlation, and the tree also, the decision tree model also found the same. Pressure was also there, it was there for a bit, and same was the case with wind direction. However, there was humidity which it has ignored. So humidity also had a high correlation, decent enough correlation, and sunshine had a strong negative correlation, but it has ignored these two things. So these are again good findings. So initially when we saw this heat map, if we had come up with a hypothesis that cloud might be one of the important features, or at least that one of these three would be an important feature, then our model also has ended up communicating the same. Now if you want to dig deeper, you can see some other things like sunshine and cloud have a strong negative correlation, which means if cloud is there, then sunshine is not going to be there. And what about cloud and humidity? Cloud and humidity also have a fairly strong correlation. It's there up to 0.6. So the other thing we can say is that, as we know, if we use things like PCA and all, it is only going to pick, it is going to remove, like sort of reduce. If there are highly correlated features, it is going to give us a new set wherein we don't have to rely on so many of them. Likewise, even with these models, if there are features that are highly correlated, it can tend to ignore those and only rely on one of them. So that could be one of the reasons why sunshine was ignored and just cloud was kept. Okay? So these are different ways you can go about interpreting your model. You can try changing some things here, increasing the depth, decreasing the depth, and seeing how these things change. There's also some different ways to visualize this. You can also include things like a color gradient for this that make it more presentable. So yeah, if any of you are, again, I keep stressing this, when you all are working on say your MLP project, if it's related vivas or even in a practical setup, focus on your presentation skills. Once you build your model, focus more on the analysis and interpretation part of it. Now, when you present it as a tree like this and give out your findings, that makes the work that you have done even more authentic. Okay. So this was the remaining thing that I wanted to cover from last week. And for the next week, we'll be working on a bit of the ensemble methods, which are models that might be built upon these different decision trees, or we'll see things like voting classifier, which takes into account the performance of multiple models. So that is it for this particular session. Do you all have any questions? Okay. So in that case, that's about it from my side.
Actually, I requested there was an email came. I think early this week.
Okay, regarding?
There is some mock OPPE or something like that. And there is a formula
Okay.
for OPPE 1 and 2. There is a formula given, something like that.
Okay. 1 second. I'll take that up. Does anyone else have any other questions related to the lecture today? Okay. In that case,
sir.
Yeah.
The one thing you showed, sir, the dot feature importance.
Yeah.
It was showing, and then what is it is returning to show the feature? Is it the score or what is this calculate?
Yeah. So feature importance, it assigns a value to these different features, as in how important were these features in the building of your model. So the way it works, it varies for different models. So specifically, if we come to decision tree, so we have to see how it calculates the feature importances. So let me present my screen again. So this is where the feature importance is present. So now if I click on this and open it, so you'll see return the feature importances. The importance of a feature is computed as the total reduction of the criterion brought by that feature. So in this case, it is Gini importance. And if we were to use the other one, it is going to be specific to that if we had used something like entropy. So there is also a warning here, which is, it says if you have too many features, then impurity based feature importance, which is something like your entropy, might not really be that great an idea, and you might have to go for a different method of looking at importances, which is permutation importance. Now,
Okay, sir. Thank you.
Yeah, so in decision trees, simply put, it is how much has that feature helped in your this one, which is why what we see in the tree and what we saw as the feature importances are both more or less the same. It is not that they're using different things. Okay, so that is why those values are matching. So you can also look it up for different models. There are a few other models that have the feature importance method. So you can look it up as to what all these different models are based on. Okay. So yeah, any other questions?
Yes, sir. Can we get the notebook link, sir?
The Kaggle notebook link?
Yes, sir.
Okay. So I've actually not made the notebook so far available because I've been prompting everyone to start working on their own. So once again, I'll tell the same thing.